Well, welcome to the final session of the Knowledge Graph seminar. Our focus today is going to be on the future, and we have a panel of luminaries with us today who are going to tell us what's new and great on the horizon for knowledge graphs. We will begin our discussion with Richard Socher. So Richard, over to you.
Hello, aloha everyone. Some crazy times right now in the world, yeah, I hope everyone is safe and America will be safer in the future. I would love to talk to you today about multi-hop knowledge graph reasoning with deep reinforcement learning, which is one part of the future. Can everybody see my screen okay?
Yes.
Yep. Wonderful. All right. This is a lot of past work and also work that is very recent and still ongoing with Victoria Lin and our group at Salesforce Research. So I'm sure I don't have to convince most of you about how important real-world knowledge graphs really are and that they're very widespread. We have a lot of them. We have old sort of knowledge graphs like WordNet, lexical database for English that's still very popular. We have newer data sets like Amazon that have a lot, and Google Knowledge Graph, that companies that collect a lot of knowledge graphs. And before I want to talk about all the work that's so important around knowledge graphs, I do want to say that I still have reservations sometimes around how much knowledge graphs can really capture all the complexity in the world in the long term, sort of, or towards AGI kinds of goals, because in the end, knowledge graphs are often incomplete and in some cases overly specific, and it's hard to know when you're in which one. So just for example, you could say country and leader, but then you might say, well, this person used to be a leader. And then you can say, okay, well, maybe there's like a past connection. And you say, well, from this year to that year. And maybe you say, well, the connection between these two entities in the knowledge graph has a set of attributes to them, like a beginning year and an end year. But then maybe somebody becomes a leader and then leaves and then becomes a leader again of that country. And then you have to have a set of time frames and so on by the end. And before you know it, you might say, what about the hypothetical? If some other person would have been president who had more votes, what would the world would look like? And then in that moment, you have to reason over different knowledge graph that includes a hypothetical and so on. So there's so much complexity in the real world in the end, and it's just so much noise that it's hard to think through ways where knowledge graphs, I think, are the final answer to really represent all knowledge in a way that allows for the complexity and the noise that is inherent in the world. That being said, for a lot of very useful facts about products and companies and lots of other things in politics, it is very useful to have concrete knowledge. And that includes things like medicine and even COVID-19, something very pressing and important right now. There are knowledge graphs around medical, or just in particular like this virus, that can be computable and allow you to, for instance, understand cause and effect knowledge and model it and then actually make it actionable and useful. So there are still a lot of domains where this is the most sensible way of structuring and storing information and making it useful. We at Salesforce, for instance, also have a lot of facts and stored in the database for a majority of the Fortune 500 companies in the world. And we continue to see the need for them to be able to access that information and to make that knowledge accessible. For instance, we have a large chatbot group that tackles a lot of interesting questions. Where's my order right now? When will my order arrive? My order arrived in a broken state. I want to have a replacement sent. And you need to be able to actually identify where that order came from and where it is right now. And that is always stored in the end of the day in a knowledge base or a database. And so we have maybe slightly more fun examples than order status chatbots and databases in this talk. One here, for instance, is a question you might ask, which is which directors has Tom Hanks collaborated with. And now when we look at this and we try to actually answer this kind of question in the chat, we want to query a knowledge base, we'll then basically can have a robot start with a topic entity that can be identified, such as Tom Hanks, and then try to identify topic relations. However, you might realize that there are actually certain answers that should be in the database and connections, but they're noisy, like I said. And so we need to be more robust in the way that we query them. And in this particular case here, we may see Tom Hanks having been a collaborator with Lydia Lloyd and Meryl Streep, who was cast in this movie. And then Steven Spielberg was the director of this movie, but somehow the connection that they were collaborators also is missing. And so what ideally we want to be able to do is still give interpretable and accurate results. And this is going to be, I think, the main issue that I will talk about, which is trying to find models that are both interpretable and highly accurate. And unfortunately, naturally, those two things are not the same. And they indeed also work over incomplete knowledge bases. So I want to start with a sort of historical, almost historical, it feels like now, some work I've done in 2013, my PhD at Stanford, on trying to embed knowledge graphs in a neural network, and then basically try to reduce the problem of identifying whether two entities are in a relationship or not with a neural network and a simple classifier. What we did here is basically embed every entity as a vector. You might think of these as word vectors, for instance, like glove or word2vec. Now you might use other kinds of models like BERT or Cove as embedding such a vector. And it can also just be initially a randomly initialized set of numbers. And so every entity in your knowledge graph has associated with it such an embedding. And then you pipe all of these three vectors: an entity, a relationship vector. This could be, for instance, is a collaborator of or has collaborated with, and Steven Spielberg. You embed all of these into a neural network architecture, and out at the end comes a standard logistic regression unit and a classification of saying yes, no, these two entities are in this relationship or not. And you can embed your knowledge by essentially training all of these embeddings as well as the neural network to identify correctly the ones that you have in your training data, and be able to say random ones, such as Tom Hanks as a collaborator of Barack Obama, as an incorrect one. They have not worked on a movie together, as far as I know. And so basically, this is a relatively simple approach. And it actually yielded surprisingly accurate results on different knowledge bases. And it's also very efficient. If you want to say, are these two entities in a specific relationship, it's a very, very fast classification problem. And there are a lot of different architectures you could use. You could embed all the words in a vector. You can also embed the relationship itself as a vector. Here, we instead had for each relationship a specific neural network that classified these. You can have these neural networks, just standard ones where you concatenate all the inputs, and you have a standard neural network layer, or you wouldn't want to have multiple. Here we added some interesting types of a neural network called the neural tensor network, and showed that this actually worked better than previous standard neural network approaches and other ones. What was also nice is that you could actually have compositional representations of these knowledge bases. So if you have tiger somewhere and Bengal tiger, those two could be combined and you'd get a new representation. And what's even more important is you could initialize these vectors if the knowledge base is over information that you also see in the free text. Then you can use word2vec and glove kinds of embeddings, neither of which existed at the time, but similar types of ideas, and actually bootstrap the reasoning over knowledge base from a large corpus of text. And that way you can make identifications and additions to the knowledge base that weren't even originally inside. So for instance, maybe it didn't say that cats have a tail, but you know Bengal tigers have tails and that tigers are a type of cat. And then that would allow you to eventually add the fact that also cats have tails. And even though that wasn't in the knowledge base initially, and maybe even Bengal tiger wasn't in the knowledge base, but that you know it's a type based on a text that you read about them. So I think that's sort of the beginning and one of the first papers that started this line of research and basically allowed us to make very, very accurate predictions. Now, since then, a lot of things have improved. Here we had, and this is what I just described in words, a very simple objective functions where we wanted to basically give a high score to the correct triplets that we do see in the database and corrupt triplets where we randomly permute one of those three, either an entity, the relationship, or the second entity, and want to reduce those numbers. And we had a max margin objective for those. And we trained all of these parameters jointly in one end-to-end trainable framework, which I think is still very attractive property of these models. But again, it worked better. Now, what's the problem with some of these, this approach? The main issue is that when you say yes or no, you can't quite say, well, based on what inference chain are you making this judgment? You can, for instance, just say, oh, well, I'd say Tom Hanks was a collaborator of Steven Spielberg because he was also a collaborator for Lydia Lloyd, and she collaborated with Meryl Streep, and she was cast in The Post, and he was cast in the Post movie, and hence I can, and, you know, he was the director of that movie, and hence I can make that inference. A neural network model would not give you such a discrete chain of reasoning. And really what we would like to do is to have a model that does the sequential decision-making the way I just described it to you. And so what we ideally would want is a model that basically starts with Tom Hanks because it's extracted that entity from the question, which directors has Tom Hanks collaborated with, and then learns to jump around in a knowledge graph and basically hop, and that's why we call it multi-hop reasoning, hop around in that knowledge graph between these different entities to make these answers and correct decisions. And whenever you want to have a model that makes such discrete actions that you can't just backpropagate standardly through it because you don't know the path of which this happens, you want to use reinforcement learning. And what's nice about this is that this will be very interpretable in terms of the results, because now you can say the model actually did these particular actions to end up in that result. And so in this RLL framework, we basically want to define our environment, the knowledge graph, and you start with some entity, and then you can go through different states and make basically actions based on the state that you're in, and eventually transition to multiple different entities until you reach a maximum number of steps. And then you say, this is my answer. And you basically will have a positive reward if that answer is indeed a correct one based on your training data set. And without jumping into too many details here, this is essentially now a much larger, more powerful neural network in terms of the policy gradient. So trying to learn a policy function that gives you the right action given the state that you're in and the things you've seen before, which essentially is going to be a large recurrent neural network, a recurrent sequence model here that feeds in at each stage the relationships and the entities that it decided on before. And then you can pipe all of this, put this all together, and come up with, again, an action space of these are the other entities that I should now jump to. And then we train all of this with reinforce and eventually end up in a couple of different states. And this is how basically the model will get rewards or not get rewards to get there. And this is a pretty general function. You can learn these various embeddings and these various functions as complex neural networks. And what was interesting here is basically that while we still embed the vectors, the entities in the knowledge graph as a vector, and we can use a lot of the power of neural networks, we also combine it with the interpretability of a discrete reasoning algorithm that is trained with reinforcement learning. And so in the end, we actually have a combination of state-of-the-art results for multi-hop reasoning, where we consistently match the embedding performance, but we also get very interpretable results, and we can see where and how the algorithm came up with the answers of, for instance, what is Laura Carmichael's profession here. We can go through, given what awards she won and what other people who won those awards, what their jobs were, and then we can give very, very interpretable answers, and in the end, correctly, make these inferences. And so I think that is kind of one of the main takeaways here that I think is also relevant for the future, which is to try to find ways in a very principled architecture to combine the power of neural networks that can, without having to feature engineer a lot about the world, make very powerful predictions, but then add ideas of discrete reasoning to them and try to learn them in a joint framework, which RL lends itself very well to. And in particular, I think this is actually something that we could use for a lot of other natural language processing problems, for things like robotic process automation and chatbots, where you sometimes need to make fuzzy classifications or decisions. You know, is this a question of order management or service or a sales question, for instance? But then once you trigger that based on neural networks, you do often have concrete knowledge that you want to fall back on. And in that case, reinforcement learning is a great step to combine it both. So with that, I hand it over to the next presenter.
Great, awesome. Thanks for that interesting overview. It's the first time I've really understood how are they embedding and using embeddings in knowledge graphs. So great description. So Mark, you are the next speaker. Over to you.
Okay. And am I sharing the right screen? Am I sharing my slides or sharing my screen?
You're sharing your slides.
All right, good. So something is actually working here. That's good. And if I go like this, that should work even better. Okay. So what I decided to do, since Vinay asked me to talk about the future, and not what I'm doing now, but what I think, where I think the world needs to go, I decided what I would really do is put a monkey wrench in this conversation and talk about the past. Because one of the things that I think is important as we think about where the knowledge graph community is going is to think about some of the stuff that has been done in AI over the past 50 years, and to remind ourselves that a lot of what people have been doing for a long time actually is really relevant to the knowledge graph community, but has not gotten enough attention. So I'm going to sort of ask a question, what do knowledge graphs really know? And sort of bring things full circle by starting actually with a discussion of the kinds of knowledge graphs we've been talking about in this seminar. And this is just sort of a knowledge graph stolen from Google, of course. And what I want to emphasize is that when we talk about what's going on in knowledge graphs in this seminar, we've all been talking about what graphs are, but I think people have been really glib about what they mean by knowledge. And what it means to say that a graph has knowledge is something that I don't think any of the speakers in the seminar has really tried to address. And that's really what I want to talk about this afternoon. So first, let me start by saying we can go back to the 70s, actually really late 60s. And as people have alluded, but no one has really dwelled on the idea, is that knowledge graphs are very akin to the kinds of semantic network representations that have been around in AI forever. And the idea of having graphs that show relationships among classes, among instances, with arbitrary kinds of properties, this stuff is old. And we spent a lot of time as a community many decades ago thinking about this stuff. And it got initially a fair amount of attention, and then it kind of drifted off. And what I know the most about, since I've been at Stanford for most of my career, is that knowledge graphs get a lot of attention at Stanford in the early 70s, when Ted Shortliff was a graduate student and Bruce Buchanan was working with him, and people at Stanford Hospital said, we need to have a system that is going to tell doctors what they need to know about patients who are being given antibiotics to make sure that they give the right antibiotics. And many of you may know that in the 70s, a system called Meissen was developed, which basically would help doctors take care of patients who had infections, where you really weren't sure what the infection was, but you knew it was bad. And you wanted to come up with some antibiotics that could help treat the patient while you figured out what was going on. Now, what's interesting is that the folks who were building Meissen started out using the semantic network approach that had been so well popularized at MIT at the time, and they realized they couldn't get very far with that approach because they couldn't get the system to reason about the situation the way they wanted to. And I picked up the idea of production rules, which were also sort of in vogue. And Meissen, as many of you know, it has hundreds of rules that will have an if side that says, for example, if the patient requires therapy for meningitis and the patient's x-ray is abnormal and active TB is one of the diseases that the chest x-ray suggests, then, well, there's a good chance it's TB. And there were hundreds of these rules. And what Meissen would do is use these rules to drive a really long, tedious dialogue on a teletype where he would ask you questions. Is case 168 a compromised host? And you would say no. How many days has case 168 had abnormal neurologic signs? 1. And you would answer all these questions, and eventually Meissen would give you a recommendation. He'll tell you what drugs you would give when you really didn't know what the infection was, but you knew the patient had to be given something until you could figure out exactly what was causing the problem. Meissen made an enormous splash. Systems like it became really very popular. Meissen was able to demonstrate that if you had a whole bunch of rules, threw them together, and you say, well, I've got a rule that will allow me to conclude the value for something called regimen. Well, if I have rules that will tell me what to treat for and what to cover for, and if I know what's significant, I can come up with ultimately a regimen that would be a reasonable thing to give to a patient. Well, when NIH heard about this, National Institutes of Health, they went wild. And this is a publication from 1979. I like to show it because I really don't know what it is. The figure kind of shows a doctor who has neurons that are being integrated with integrated circuits, and they go to a mag tape. I don't know what's in the photo, but it shows you how excited people were in medicine about what expert systems might do if you could actually encode all those rules. And we obviously know that during the AI hype of the 1980s, everybody was all excited about how these kinds of systems could possibly replace a lot of the kinds of reasoning that people were doing. At the time that all this was going on, and this was admittedly 40 years ago, there was a lot of confusion because people realized that creating by hand systems of all these rules led to systems that weren't really maintainable. People who were trying to build semantic networks were getting something which they thought they could at least visualize better than a large rule base, but the kind of inference that semantic networks could support were pretty primitive. How do you know what representations would give you the smarter system? And there was just enormous bickering about what is the right way to represent knowledge. Now, what does this have to do with knowledge graphs? Well, around 1980, Alan Newell was the president of AAAI, and at the very first AAAI meeting gave a presidential address, frankly, that nobody understood until about 5 or 10 years later. But what Newell said at the time was really interesting, that we should stop bickering about how to represent knowledge. It really doesn't matter as much as trying to understand what knowledge a system might have rather than how that knowledge is represented. And what Newell said is that knowledge is not something that you put into rules or you put into a graph. Knowledge is behavior. And he was a psychologist, so he had the right to say that. And that behavior was something that an observer would view and attribute to the agent as representative of knowledge. So in Newell's idea, we had symbols that we could use to represent knowledge. We had hardware that could implement our programs that included all these symbols. And above that was this ethereal knowledge level, which was the behavior of the agent. And the knowledge was not something that you encoded in a rule or in a graph, but something that you observed. And in Newell's vision, knowledge was a competence for problem solving. It was not something you could ever see or write down. It was never something that you could be certain that the agent knew, but it was something you would attribute to an agent because the agent would appear to have goals. It would be able to have actions, and it would select the actions that would seem to be best at allowing that agent to bring it toward its goals, and it would behave rationally. And so in Newell's view, what we really wanted to be doing is not arguing about how to represent knowledge in graphs or rules or first order logic, whatever our favorite representation system was. We wanted to be thinking about that behavior and to understand intelligence at the knowledge level. And for a while, there was a big buzz about knowledge level analysis, which is not how to encode knowledge in a particular representation, but how to understand intelligent behavior in terms of the goals that an agent might have, the actions that it might select, and how to select actions that allow it to achieve its goals. It required a language for talking about goals and actions, and it made the whole idea of knowledge representation kind of secondary. That was all great. People loved the idea. But then what the hell is knowledge level analysis and how do you do it? And that became a really difficult challenge because people didn't really understand what it would mean to represent something at the knowledge level. We all can understand what it means to have a graph. That's a representation that's pretty clear. But what does this tell us about an agent, about what an agent knows, and how to infer what those behaviors might be in terms of goals and actions? Well, an interesting analogy, which I like a lot, is that a knowledge representation is kind of like the following. What I show on this slide, some people look at this and say this is music, but it's not music at all. What you see on this slide is really a bunch of representations. It's a bunch of notes. It's a staff. It's a bunch of symbols. And we know that there's a process that can be applied to these symbols that will generate something that we can all hear and we can appreciate as music. And the idea behind knowledge level analysis is quite analogous. We can have a representation like a knowledge graph or a bunch of rules, but until we can apply some process to that representation that performs inference, all we have is a representation. The same way we can have a representation showing us a bunch of notes, and until we have a process that we can apply to it, we won't have the experience of music, which is not representational, but which is oral. So we go back to the idea of Meissen. What we see in Meissen, it could be perceived as a bunch of rules, and that's what the people who built Meissen talked about it. And people would look at Meissen and say, I know what Meissen knows because I know all the rules. The same way people now say, I know what my knowledge graph knows because I know what all the nodes and edges are. Well, around this time, a guy named Bill Clancy came around and said, you can look at Meissen as a bunch of rules, but you can also view it in terms of behaviors. You can say that Meissen does something called feature abstraction. It takes data about a patient, like the white blood cell count, and it generates abstractions of those data and says, this patient is what you would call a compromised host. There's something wrong with this patient's immune system. And patients who are compromised hosts often have gram-negative infections, which might be caused by bugs like Pseudomonas or E. coli. And so Clancy said, look, let's think about things at the knowledge level. Let's think about things in terms of behavior. Let's say we have an agent that wants to take information about a patient, abstract it, identify on the basis of those abstractions what the possible solution set would be, and to refine the solution based on available knowledge. And that was heuristic classification. The same problem-solving approach that was used in a gazillion systems that occurred at the time. Here's one called Grundy that Elaine Rich developed at UT Austin, where Grundy was an expert system. Someone walks into a library, describes what kind of a person they are, and somehow the librarian is able to make some judgment and perform some sort of stereotypical reasoning and says, well, this kind of person likes romance knowledge, this kind of person likes do-it-yourself books, and basically using feature abstraction, heuristic match, and solution refinement, the system would basically apply a problem-solving method and make a recommendation about what kind of a book you wanted. Well, these problem-solving methods like heuristic classification were used to represent stereotypical problem-solving behavior. They made explicit what were the roles in which knowledge got used during problem-solving, and they provided a set of building blocks for composing these abstract procedures. And they're important because you think about the Meissen task, give me a patient with a presumed infection and I'll tell you what the antibiotic should be. You could imagine if you were to build Meissen now, you wouldn't use rules, you wouldn't use the traditional knowledge graph, you would probably have an ontology of antibiotics and organisms and patient characteristics and map it to some kind of a problem solver that would operate on that ontology and give you the kinds of information you needed to know how to treat the underlying infection. Well, in the 1990s, and this is what everybody forgets, there was enormous activity to come up with problem-solving methods that would allow us to be able to understand problem-solving activity at the knowledge level. People built classifiers. They built systems for fault diagnosis, for constraint satisfaction, for planning, for design. And the idea was to take these problem solvers, understand how they might map to ontologies, and to build systems that would be understandable at what Newell called the knowledge level. So you understand in terms of the problem-solving behavior, how an agent could actually meet its goals. And one way in which you would actually build such a system would be to say, look, let's identify what is the task that we're trying to solve. We're trying to diagnose a patient who has presumed infection. We're trying to schedule time on a flight simulator. We're trying to build some sort of a system and take into account certain constraints. The idea is you would have a task, you would have a problem-solving method that might solve that task. The problem-solving method itself might entail subtasks. There might be problem-solving methods that could be used to solve those subtasks. And ultimately, the people building expert systems at that time said, look, we can do this for anything. We can do it as something as mundane as doing your laundry. We can say we want to do laundry with the laundry method, and that can have subtasks like sort your laundry or put your stuff in the washing machine. The idea is that anybody trying to do something intelligent, anyone trying to use actions in order to reach goals, would be able to use problem-solving methods and this kind of task decomposition in order to build a structure that would allow us to reason about the system at hand and to be able to implement things so that we could, first of all, understand at the knowledge level what are the processes that matter and how do those processes lead us to our goals, and then how can we actually implement that in terms of some representation. Well, around 2000, suddenly the semantic web became the next new thing. And the community that for the past 10, 20 years have been working on ontology and problem-solving methods and understanding knowledge level analysis suddenly got sucked into, well, maybe that's being too pejorative, but being jumped on the bandwagon of the semantic web. And this is the Scientific American article that many of you may remember from 2000, where the whole idea of the semantic web when it was first presented was all put in terms of intelligent problem solving. That the semantic web was going to give us intelligent agents that could book our flights, could shop for our clothes, could basically do anything, could mow our lawns, do whatever was necessary. And frankly, it became really exciting to think about what agents on the web might mean. But the world over the past 20 years or so has been shifting radically. And so, yeah, we had the semantic web. And people really got excited about the kinds of agents that could be put on the web and what would happen if we had web scale knowledge representation. But for whatever reason, the semantic web community began to downplay the agents, began to downplay the ontologies, and suddenly we're really focusing on linked data. And then the linked data mainly kind of morphed into knowledge graphs. And now we're in a world where everyone is focusing primarily on the knowledge graphs and forgetting where all of this came from. What that means is that our knowledge graphs now are not all that different from the semantic networks that we were touting in the early 1970s. And we're in a situation where really we've kind of forgotten that there was a whole period of time when people were being very critical about understanding problem solving and understanding behavior in ways which could lead us to the representation of knowledge, or rather to the development of systems that could manifest knowledge, where we understand knowledge in terms of behavioral manifestation. Even Jim Hendler, who was a co-author on that original semantic web paper, kind of posed rhetorically, where have all the intelligent agents gone? And have recognized that we think so much now in terms of representation and ontology that we forget that the reason we got into this game in the first place was because we really cared a lot about behavior. Now, our knowledge graphs as they exist now really do absolutely wonderful things. And you've heard so much about this over the past quarter in the seminar. Our knowledge graphs can perform indexing and search. They drive all kinds of wonderful chatbots. They can manage catalogs. They can link advertisers to consumers. They do lots of great stuff. But they don't drive general purpose problem solving the way many of our systems 40 years ago did. And I think what's really interesting to think about is that because of the way our whole way of thinking about the world has evolved, we have held on to the semantic networks that were so important in the 1960s and 1970s. But I think we've really forgotten about how we can use some of this stuff as the basis for building intelligent systems that are not really doing the kinds of things now that even 20 years ago they were capable of doing. I mean, as I said, who'd have thunk that we're now representing knowledge as graphs when people thought in the 1970s that's kind of passé. The good news is that knowledge graphs are wonderful. They really have much more capability. They have much more scalability, they have much more size than the old semantic networks did of the 60s and 70s. But the disappointing news is that by themselves, just a graph really can't do anything. That just like musical representation, we have to apply a process to the graph in order to get any kind of behavior out of it that we might call interesting. And then if you ask me, what is the research opportunity? I think we can actually represent knowledge as graphs and do incredibly great stuff, as you've learned about in the seminar. But we can also remember that, we used to do a lot of other stuff too in AI, and we can start to apply processes to these graphs to generate intelligent behavior in ways that people who are currently working with knowledge graphs just really haven't dreamed of. And so when we think about what we're learning about in the seminar, certainly we all understand what graphs are, but it's important to remember that knowledge is a behavior. It's a behavior that has characteristics that one observer attributes to another person or another intelligent agent. And to say that we have knowledge in a graph really means that we have to be able to say that that graph is capable of behavior that we would interpret as allowing an agent to be brought closer to its original goals. So when we look at a knowledge graph, typically we can see relationships that tell us how classes relate to one another or how instances relate to one another. We understand the edges, we understand the nodes, but what we really want to be able to do is start thinking about the graphs as capable of generating behaviors, thinking about what is the music, if you will, that comes out of the graph. And for that, not only do we have to bring back our understanding of graphical representation of knowledge, which is 50 years old, but we also want to start bringing back some of our thoughts about reasoning and problem solving, which I think are incredibly exciting areas of research, which somehow have been clouded over by all the excitement that the graphs themselves have garnered in the past few years. And let me stop with that.
Well, that was awesome. Thanks, Mark, for such a thought-provoking presentation. That's exactly what we needed. And we will obviously convene together as a panel to talk more about some of the issues you are raising. We will move on with the next speaker, but Mark and Richard, there are some questions waiting for you in the Q&A panel. If you feel so inspired, you can start answering those questions if you like. But for now, we will move forward with Guha. Guha, over to you.
Should we wait for them and at the end when you video, or go for text?
So the questions which are in the chat, if you think you can just type in the answer, you could do that. And if you feel we need to take them up at the end, we can do that also. Go over to you.
Okay, can you hear me?
Yes, we can hear you.
Okay, so I'm going to talk about data commons. This is a project that we're working on in Google. It's kind of related to knowledge graphs. It also touches on some of the points that Mark was making. The context is that data powers everything. Policy, journalism.
Did you want to go in slideshow mode, or this is how you wanted to continue?
I have a bunch of things to show you, so it's easier for me to switch tabs.
That's fine.
Yeah. So the question is, how do we make it easier? The problem is not a shortage of data. We have data about demographics, for example, from census, the ACS, We have data from economics, BLS, Bureau of Economic Analysis, World Bank, OECD, about health from CDC, and many other sources, climate, genomics, and so on and so forth. The real problem is that there are too many formats, too many schemas. The current model for using data is that whoever wants to answer a question goes around foraging for data sources, tracking down assumptions in the provenance, cleaning it up, downloading the whole thing, cleaning it up, compiling it, figuring out storage. There are very high upfront costs. The ecosystem is still relatively sparse. There are not that many tools. The situation is analogous to the situation with satellite imagery circa 2004. In early 2004, Landsat had most of its imagery up on the web. If you wanted to figure out what your house looked like from the sky or what your school looked like from the sky, you could figure out where to go download which tiles, get some software to stitch them, and get an image that should give you your answer. Google Maps arrived, and it suddenly went from less than 0.01% of the world doing it to it becoming almost a birthright, and everybody was trying to figure out exactly what their houses, what their states, what their cities look like from the sky. We want to do something similar for data. Imagine today if you wanted to get a correlation between the actual correlation between poverty levels and COVID fatality, or what has been happening to the Bay Area as African-American population or Hispanic population as tech has grown. You could, in theory, answer these questions if you had a week or 2 or 3 to spend. Imagine instead if you could just ask Google or any one of a number of public sources. That would be great. As a first step, what we've been doing over the last couple of years is taking a wide range of data sources, including some of those mentioned over here, actually including all of those mentioned over here, plus a bunch more. And we've built a single big aggregated knowledge graph. It's not just a set of data sources. We've gone, downloaded the data, cleaned it up, normalized it, come up with a vocabulary for the whole thing, and created this large knowledge graph. Of course, since this base is way too big for most people to download, we provide APIs on top of which people can build applications for students, journalists, researchers, and many more. It's an important thing to distinguish between data commons and sort of collections of data sets. There's many collections of data sets out there, ranging from the NIH data commons to Dataverse, and Google itself has a dataset search. These collections often solve kind of the problem of finding the data set. But the remaining problems, cleaning, joining, normalizing, and all that still remain and make it, put the solution way out of reach for most people. Data commons is different. It's a single KG which is being built by joining all these data sets. The first version of data commons is a substantial portion of it is about people, places. So we have all of these data sources listed there. On average, about 5,000 variables for every state, county, zip, school district, congressional district, and so on. There's also sort of vertical specific data commons having to do with botany, and another one having to do with bioinformation. There's APIs to the whole thing, REST APIs. It's tightly integrated with Python and Python notebooks. And also everything I show you today, you should be able to access from datacommons.org. There's Sparkle APIs. There's even a Google Sheets API. There's applications for 4 categories of users. One is researchers and students, then it's journalists, and then finally, the average end user. But I'm actually not going to talk about that today. So let me just go into a few of these use cases. The first use case is for there's several million students of data science today in the US alone. These data science students learn many different methods, but most of the data they deal with is toy data. And as much as I love the next Twitter data set, at some point it kind of gets boring. This is an assignment that is used in DS100, which is the upper division data science course at Berkeley, where the students are asked to build a model of obesity across 500 US cities as a function of blood pressure, unemployment, and poverty levels. The data for this comes across 3 different federal sources, which use different indices, different ways of referring to places and things like that. CDC, Bureau of Labor Statistics, and the census. This would be a sort of a multi-day at least project in normal, if you were to start from scratch. But if the platform comes with all this data, it makes it feasible. So this is blood pressure versus obesity. This is unemployment versus obesity, and you can see the correlation. And this is the sad correlation, poverty versus obesity. What is interesting is that if over 400 students complete this assignment for grade in under an hour. And that kind of illustrates the core point over here, which is that if we could bring that level of tool, that level of, if we could reduce the time to go to test a hypothesis from on the order of days to order of minutes, more interesting stuff will happen. This tool still requires people to write code. And as we know, not everybody knows to write code. This is a different tool which where people can go explore these different variables for these different places. So if you can pick a place, and these are all different, this is a big tree of different variables over here. The thing which you're interested in right now is to look at Santa Clara County versus Imperial County, the richest versus the poorest counties in California. And with this, we can see how different the median income is. Given these times, however, what we're interested in is not so much median income, but COVID. What's happening in these places, these 2 counties in COVID? You can see how Santa Clara County is way up there. Imperial County is not so way up there, is trailing. That stuff looks good until you look at the per capita numbers. Then you see what's really happening, right? And you can pull in any other county over here. Let's pull in Los Angeles County. There you see Imperial County is even worse than Los Angeles County. I wonder how it compares to, I don't know, Cook County, Illinois, which is also in one of the worst shapes. It's not as bad as Cook County, which is a good thing. And so this kind of analysis goes from on the order of, well, you have to wait for the New York Times to do it, to making something that is available for everybody trivially. And one more just demo before I have to show this. This is, again, a correlation tool. This is a correlation between across cities in the California of the population that is never married versus violent crime. Each dot represents a city, and you see there is a correlation. And this, let's assume you want to try the correlation for the population that is married, and you see it's inverse correlation. There's thousands of variables that you can compare against, and this kind of analysis is now made available quite trivially. Now, of course, these tools are nice, but they, again, are limited. And so there's a new generation of things we're building, and this is to be used. And so this looks like a normal Google spreadsheet, except what is interesting, if you look at the function line, is that we're building into Google Sheets the simple function called dcget, which can just pull out data points out of this giant graph and populate them into Google Sheets. Actually, Jo Baylor in the Stanford, I think she's in the School of Education, is working with a bunch of people to create a set of courses targeted at high school students, so that we have high school data literacy being brought into high schools in a big way. Now, let me go ahead and talk about a different data. This is all this data that is there about census and economics and health and so on. There's other vertical specific data commons. This is one which is around biomedical data. So this has data from, in addition to data from CDC about related to health, it has data from DBSNP, ChemBale, UniProt, NTRES, MESH, and so on and so forth. This data graph, this is actually even bigger in size than the one that has to do with people and places. These are, and this is being built largely by with help from a collaboration with Samantha Picos, who's Tony Oro's PhD student at Stanford, and with the research group at UCSF. So these are all the data sources it has. This thing is a giant beast. And the best way to describe why we would want to build something like this is to go through a single example. Life in sort of in a grad student's a day in a grad student's life consists of answering questions like this. They're trying to answer, given a list of genetic variants, find the clinical significance, the functional category, and specific gene associations in whole blood. If all the data that is required to answer the question is on a single site, and that site provides some kind of a fancy search function, they can use that. The typical option is to download the data from these different things, parse it, build some kind of a tool, and get the answer. This is, in this particular case, Samantha says that it takes her, she has to download ClinVar, that takes a few hours, then download dbSNP, a couple of days. Actually, you typically download a portion of that, and you take the portion and you write Python code in order to combine the two, and you put it somewhere and you run the analysis. And so the whole point is that if you had, if you're going to take on the order of a week to check each of these things out, and maybe you can, after some time, you build yourself a tool bench. It's very, very cumbersome. This is the query that she issues to Data Commons. It takes about 20 seconds to run. It goes through several petabytes of this data, and it gives it an answer. And right now, what she's doing, along with a bunch of other students, is building a layer on top of this so that they don't have to understand query languages like Spark. There are other data commons that are being built. There's one around economics that we're starting to build with folks from the economics department at Stanford. There's one that is being built just around COVID. There's one that is being built in collaboration with Arun Majumdar and Sally Benson in the Precourt Energy Institute at Stanford, what is called the Energy Atlas of the US, which includes not just all the energy sources and energy and sinks of more than a certain size, but also as much of the EPA data as possible, so that we can start building better models of what on Earth is going on, which is especially important as you get more and more and more renewables into the mix. So let me just talk about a couple of minutes about the technical challenges in building something like this. There's various categories of challenges. I'll just say a few words about it, and then I'll leave with a few words on these KGs. There's representation issues. As Mark mentioned, the concept of putting nodes and arcs between them has been there for a long time. It kind of died. It made a resurgence in the mid-90s, well before the infamous Scientific American article. And it came up as MCF and then RDF. It came up in the context of representing metadata for the web. And then there was the paper which claimed that we were going to be able to have AI in a short while. Of course, everybody went there. And then when it became clear that that wasn't going to happen, there was a need for having structured data on the web. And these knowledge graphs became a way of, essentially, there's a databases with runtime extensible schemas. When we wanted to build something serious like this, it's not enough. The kind of like, I'm going to have a bunch of nodes and I'm going to have put arcs between them is simply not enough. You can't just say that, Jerry Brown was the governor of California from this time to this time because he was governor, then not governor, then governor again, and so on and so forth. And there's many issues. So there's issues with representing time, with representing geography, with measures, provenance, and then something like Data Commons, which deals a lot with statistical aggregates. Many of you are familiar with the problem of these incredibly long predicates, which capture a huge amount of semantics, but the system doesn't understand. So if you want to know the male Latino population under 26, you can't have a predicate called that, which is what people do. Triples are easy to understand, relatively widely understood, but real systems need more expressiveness. This is a whole one range of complexity. Another aspect is Data Commons, even as it is today, and we're getting ready to get much, much bigger, is huge. It's more than about 50 billion triples. The bio part is another 100 billion triples. And there's a wide range of queries. Some of the queries that I showed you in the graphs are simple queries that are actually not that simple, but they require responses on the order of milliseconds. There's this complex Sparkle query that I showed you, and there's things in between. The data commons approach to this is that we don't have a single store, backing store. We don't have just a single representation of the whole thing. There's multiple backing stores that support different classes of queries with different latencies. Everything ranging from BigQuery, which is capable of handling petabytes, to in-memory hash tables, which have incredibly low latency. So what is the KG there? The KG is a view. It's I hate to use the word knowledge level because I never understood what it meant, but I'll use a phrase that was coined originally by my advisor, but that we then adopted in Psych to mean something slightly different, which is that you have a directed labeled graph, you add function terms, you have this thing called context or microtheories, and a bunch of special kinds of inference, not full first order logic or anything like that, but limited classes of inference. And how do you actually say what is in the system? And for that, we have some kind of a specification, and this is the epistemological level, this whole thing. And for what it's worth, this is a complex, you can interact with it in these languages like Sparkle or GraphQL, which are the epistemological level, or more specialized APIs, which then gets translated, and if depending on which is the fastest layer which can answer it, those things get served up. So let me just end with some ending thoughts. Just a couple of issues. So some real issues that come up with building these big knowledge graphs. Vocabulary tree. Google's KG, Scite, Wikidata all have many tens of thousands of these schema terms. Human language manages to do this only with a few thousand terms. And that's because natural language has this amazing compositionality, and the challenge is to bring that to knowledge representation. Recent approaches like embeddings and so on, which Richard spoke about, are fascinating, but they don't come with the kind of hard guarantees that traditional logic do. And while it's not important or necessary to have these hard guarantees for certain domains, for other domains, like if you're trying to figure out, roll up some aggregates about COVID hospitalizations, you do want these guarantees. It would be fun. This is an open area where, in order to really scale these graphs to cover, and by use the word graph, I mean graph with a bunch of inferencing abilities and so on and so forth, we need to be able to solve this vocabulary problem. The other thing is the classes of inferences we talked about and that we can do even in something like data commons are incredibly limited. There are a number of old AI problems that had been identified. And nobody talks about them anymore. And unfortunately, it's not because they're being solved. It's because they can't really be expressed in today's machine learning formalisms. And I'll leave you with just one example, which is a frequent topic of discussion in Google. You can ask Google or Bing or any of your favorite search engine, what's the world's tallest mountain? And they'll happily give you the answer out of their knowledge graphs. Try the same question. Try the question, what's the world's tallest mountain yesterday or day before yesterday? And these things really don't have the concept of they don't have the ability to express these things. So with that, I will stop presenting and we can take questions.
Well, excellent. I thank all the speakers for their excellent opening presentations. We can take questions. And Naren, do you want to pick something?
Yes, sure. So there are a lot of questions for Mark, and he has indicated that he would like to answer some of these questions live.
Okay.
So Mark,
I tried to answer online, and I lost my text box for whatever reason. So we'll do them orally.
I also kept it pretty short, and happy to go into more details on any of mine.
Sure, sounds good. So let's, Mark, maybe we can start with a very specific question for you. Why are you using mesh as a data source? It's a thesaurus and is used to describe the contents of biomedical literature.
I think that was for Guha.
Yes, you're right. Guha.
Oh, it's for
Yes.
me. Yes. Okay. So we're using ICD-10 right now. And there are, one of the things that you can start getting very familiar with when you actually try building these large things and providing APIs to the world is licenses. We would really like to use SNOMED and all that, but it just, the license terms just don't allow us to do that. So we start with ICD-10 and we're actually trying to figure out what is the biggest thing that we can actually go after.
Okay, very nice. Actually, Go, I had a question for you. So very nice framework. Is there an option to use this kind of framework inside a company, inside an enterprise for their own data? Because at companies like JP Morgan, we spend like $2-3 billion on data sources.
Yep.
Okay.
Yes, there is go@google.com. I'd be happy to put you in touch with the people who will do this. Yeah, I just didn't want to go. It started off with an effort to, the number of times that people have to take these, download these data sources, clean them, join them, etc., is painful, right? We had it once. There is a single large database which runs the internet, is the DNS database. At one point in time, in the early 80s, people would download that database and install it, and every week or so update the database. Can we do, and then of course we have the current version of DNS, can we do for all of this data that comes from the Commerce Department, from the health departments, and so on and so forth, and just make it like that? That would be really nice. That's what we're trying. But of course, the intranet thing, it's actually fascinating because the way it's architected is that you can layer your intranet data on top of this big giant graph, much like the way we layer our intranet on top of the external internet, so that all the entities, all the data about these entities, etc., are visible to you together and are joinable with your internal data.
Okay, thank you.
Mike has a question.
I have my question for Guha. I was looking at your list of sources, and you know, one of the things I think is exciting about knowledge graphs is that there is very specific data that's often being recorded there. California is a state in the United States, and it's North America by and large, and so forth. And so you've got a lot of sources there that have that kind of information. But then there's more general common sense information. I don't know if you've ever heard about a system called Psych. And I'm just curious what you're
trying for the last 20 years to forget it, 25 years to forget about it.
So you comment about that kind of general purpose common sense information. Does that have a role in a knowledge network or not?
This is what I was alluding to with my very last comment, which is you go ask any of these beasts, what was any of these, I'm sorry, search engines, what was the tallest mountain yesterday? They can't answer that.
Yeah.
At the last Super Bowl, Google ran this ad for this product or this thing called Memories, where you tell it things and it remembers. Fantastic. And the question is, can I tell it things and have it remind me in a really intelligent fashion, right? If you go back to Alan Kay's Knowledge Navigator product video, can we actually make those things happen? And it's fascinating now that, you know, if you look at the total amount of money spent on site, every few weeks, that much money is spent on AI across the big companies today. It's maybe we can have another shot at building these things. One of Psych's main problems was that Doug and was complicit, I guess, refused to get grounded in any actual practical thing because it had to cover everything. No, one of the things is you have to be grounded in things, but multiple things that are actually going to be useful, because without that, you know, it's not going to happen. And I would love to chat with, I don't want to derail this thing, but there is, I think, a path towards making our knowledge graphs far more than just flexible runtime schema extensible databases, because that's all they are today.
One thing that's really interesting around common sense knowledge is that it's surprisingly accurately and well captured in language models these days. Neural network language models that just train on billions and billions of documents to learn to predict the next word. So very large, powerful deep learning sequence models. We've released one that for a while was the largest one, with 1.7 billion parameters last week. OpenAI released one with 170 billion parameters. and they read all of Wikipedia, obviously, but you know, millions and millions of more web documents from Common Crawl. And if you say, like, how many legs does a cat have? It'll just like, or a cat has like how many legs? It'll just generate the answers, which is really surprising. And you know, like the class was pushed off the table. Then it'll just autocomplete, fell, broke, spilled, and like says all of these different things, and has captured now all of this common sense knowledge in a way that we can retrieve it and query it. And that really changed, I think, a lot of people's minds about maybe the right approach is to not make it explicit, but let these large neural nets kind of figure out what common sense and knowledge is, and then we can still read it and make it actionable.
Okay.
Yeah, it would be good at some point to put it through. McCarthy used to have these examples which were really succinctly put. You have this coin which says 20 BC. What's wrong with it? I'm really looking forward to the day when these neural network models can tell me what is wrong with that.
What is wrong with, sorry, 20 BC?
Yeah.
Can you elaborate a little?
You know, coins have dates on them.
Yeah.
The coin which says 20 BC.
I'm not familiar with what you're talking about. Sorry, is it a coin?
Yeah, it's you know, coins. It's like you take a coin.
Oh, before it was, oh, I see. And on the coin, you anticipate that at some point Christ will be born, and that's not possible, and so on.
Yeah.
Exactly. So I think the other sort of indirect result of
there's a whole range of, there are problems which can be captured by, yeah, there's.
Here's a good question, very relevant to what you're discussing now. So Richard, there's a question for you which you answered, but maybe you can go over it live. So Richard, did you try to compare the neural tensor network-based predictions and how to merge it with some logic-based inductive reasoning or something? Do you want to elaborate more on that?
Did not compare with pure logic-based inductive reasoning. I guess it's a little tricky to try to do that, especially when the data set includes a bunch of relationships that weren't really in the training data. And the only way you could then make the leap about, say, Bengal tiger you've never seen in the training data, but you know it's a tiger from compositionality, and you know that tigers have, you know, legs and things like that from the text, to then make that and add a, like, tigers being a specific type of cat, and cats have these things and so on. It would have been really hard to try to do that with logic, just mostly because logic wouldn't have access to all of that knowledge from the text that is kind of there in a fuzzy way. And now these language models are capturing this even more powerfully than just the word vectors themselves did before.
Okay, thank you. So here's a question for Mark. What is your opinion about the role of recent representational learning techniques in the context of knowledge? The first question in the tab.
Well, it just means that the problem becomes more meta, that I think learning in general, I would say, it can be construed as a problem of intelligence, where one has a goal of trying to infer something from data. And so I guess if I understand the question right, I would just view this as a way of recasting how an observer would construe any kind of a learning challenge, whether one's learning representation or anything else.
Thank you.
Okay, I have a follow-up question for Richard. So Richard, isn't it the case that the common sense knowledge that these language models are learning is limited to the knowledge which exists somewhere in the document? If there is a piece of knowledge that has never been written down, there is no way this language model can actually learn.
That is actually surprisingly not the case anymore. They capture more things than are just in even the convex hull of the things it has seen before. It can make various combinations and have like autocomplete sentences, like you have a 8-legged spider or like a 15-legged spider or something weird it's never seen before. And then you ask, can it still walk? And it'll probably still say things like, yeah, it'll walk around. Like it's surprising how robust they are and how much they capture the common part of common sense. Like it's, they can generalize much better than even I had thought like 5 years ago they could to unseen hypotheses. Of course, the main problem that they have is that they can generalize and sort of generate the next couple of like 10 to maybe 50 words that are sensible given what you started out with. But as you let them generate for longer and longer, eventually they might repeat themselves, they might contradict themselves, and they don't have this beautiful sort of, this knowledge is immutable and it's like always true kind of sense, and they might eventually not make sense anymore. There's always like a short period, and then they have their state gets lost. And so that's sort of where you might then want to bring in either retrieval or knowledge-based kinds of methods and merge them with that. We see similar things in question answering where you want to question, you can answer a lot of questions now by just essentially memorizing the knowledge base with some neural network form in some fuzzy way. But then it makes certain mistakes that if you had a retrieval-based methods or knowledge-based method that would incorporate some like true facts that are always there, it would be more accurate. So I think that's sort of where, in my eyes, the most interesting part of the future lies. Like, how do we balance and learn in some end-to-end fashion based on some objective function to merge logical reasoning with all the fuzzy and complex and common sense and probabilistic types of reasoning that we see in the world in a way that really scales to all the complexity that we see.
And so based on the recent events, Richard, do you think the system can learn like morals and humanity-based rules, like not harm anyone or those kinds of things?
Boy, I think you know, any AI system is only as good as the training data that we give it. So if we see training data like Westworld, then it'll be a model like what we see in Westworld. If you give it better training data, unfortunately, humans, we wouldn't want the ethics of humans to actually generalize, because we're not very nice to all other entities that we don't deem as smart as we are. So we would only hope that we'll give out the best, our best attempts at ethics to these kinds of models.
Mike, you want to say something? You're on mute.
You're on mute, Mike.
I wanted to talk with Mark for a minute. Thanks for reminding me. So I really loved your presentation. I thought it was putting our finger on a very interesting topic that had been overlooked more or less to a very large extent in this seminar so far, which is, you know, where's the semantics, where's the meaning, where's the knowledge? But one thing that bothered me about your presentation, although it was very appealing, it almost convinced me, was like the music example was, you know, the behavior, your emphasis on behavior.
Yeah.
And in those years that you were talking about, there was a lot of discussion about the distinction between the data, the facts that are true, which is what was in the semantic net, and the knowledge, which was what do we do with that semantic net in your view, which is behavior, but also what can we conclude from that semantic net, and it's not so much necessarily behavior. So I wanted to, it's all by way of introduction to John McCarthy's view, which is that it should be behavior independent, that there are declarative interpretations of the data that rise above the ground facts. He would often give, he used to give an example now, the fact that if you make two objects collide with each other, they make a noise. Now that's a fact, that's a piece of knowledge about the world that can be used for many purposes. If you want to wake somebody up, you knock things together because it'll make a noise. If you want to avoid waking people up, you make sure things don't bump together. If you see two cars come close together in the distance and you don't hear anything, well, maybe they didn't collide. Or if you do hear something, you guess they did collide. One fact, one piece of information about the world, I don't want to say fact, that's not quite right. That one piece of knowledge about the world can be used for many behaviors. And so, but your emphasis on behavior suggests that somehow it would be task specific, that it would be useful for only one thing. Anyway, I thought you might comment on that.
Yeah, no, that's a really good point, Mike. And I think the issue stems from the fact that in our vernacular, we don't make much of a distinction between knowledge and intelligence. And in talking about what Newell refers to as the knowledge level, he's actually referring not so much to knowledge specifically as he is to intelligence. That it's the ability to observe the agent and to infer that based on what you are observing, you construe the situation as a manifestation of intelligence, and therefore the agent must have knowledge. So yeah, if you have an axiom deep in your system that tells you when two entities collide, they necessarily make a noise, at least in the absence of a vacuum, then that's a piece of knowledge, which is a term I hate because I don't know what a piece really is there.
Right.
But it's different from looking at an agent's behavior and construing that it has intelligence. On the other hand, in order to display intelligence, you must have what Newell himself called a body of knowledge, which would be a bunch of facts of the kind that McCarthy would view as being the essential primitives.
I have a question. So, because we got some common sense stuff, there's the Winograd schemas, right, which some people say capture common sense, and again, surprisingly, these neural networks have now done super well. They used to be like, yeah, they will never be able to do that, and now we get like 70+% accuracy, 80% almost, I think, in some cases with the newest models, and humans get around 93. These are just, for those not familiar to students, like examples like you say a sentence like the trophy would not fit in the brown suitcase because it was too big. What was too big, the trophy or the suitcase? And you have to, correctly say that the trophy was too big in this case. And so, but you could also say the trophy would not fit in the brown suitcase because it was too small. And then what was too small? And then you'd have to, make that inference. And so I don't know how you would do these kinds of things with knowledge bases where, this is just one case. And of course, for one particular case, you can make a knowledge base of all the things in suitcases and in travel, and, but then it gets hard once you extend it to all the other stuff.
So Richard, I'm not sure I understand the thrust of your argument. If you're suggesting that there are things that cannot be done by logical encoding of knowledge, I don't think anybody here is going to disagree with that point. There certainly are things that cannot be done that way. The question is, can everything
one particular point about that particular class of queries? There was a period of time when Johann de Cleer, Ken Forbes, and all of these guys basically went after the very sophisticated things having to do with you toss a ball up, it comes down, you toss a ball up, and will certain classes of shutters work in space and so on, modeling these things and doing fairly detailed reasoning with it, and it was called qualitative physics. So it's not as though these problems have not been tackled. And then congratulations on being able to solve more and more of the Winograd schemas with just sentence completion. It's quite amazing that you're able to do that. But it's not as McCarthy would say, it's not a this versus that. It's like this. It's right. Just.
Yeah, no. My hope is like that we'll kind of combine these different models and model families. And the question is sort of how. Like I still don't quite have.
No, yeah, actually, I was going to say you're asking how. I was going to say read the papers by de Cleer and Forbes. They'll tell you how to do really, really complicated model building things. Based on basically it was called qualitative physics. So.
I guess to me,
on the subject of how, one thought that triggered in my mind based on the presentations was that, well, Mark is talking about these ontologies and Richard was talking about these embeddings. So one way to combine things is that, well, you have an ontology, but in the node of each ontology is not a concept, but it's a word vector, right? And I think that's kind of what knowledge graphs are, knowledge graph embeddings, that's the kind of idea they are pushing. I don't know how far that can be pushed to ontologies in general, where we have a symbolic ontology, but each node is also grounded in some word vector or some numerical representation.
Yeah, and I guess my hope is that there's somehow that the AI model can make those inferences and learn the logic as part of its objective function.
Right.
And that's one of my hopes.
Also, this comment by Guha that the money spent on AI these days is greater than total amount of money spent on psych over 30 years. I mean, that's very telling. And it just boils down to, well, if you try to solve a problem that somebody has and somebody is willing to pay for, they will spend incredible amount of money to get that problem solved. And that's kind of what's happening with some of these deep learning models, and even some of the knowledge graphs that we are seeing. They are addressing some real business problem or real user need that people have, and people are willing to invest so much resources to investigate techniques that would help them solve those problems. And the challenge we've had with projects like Psych is that they're not really connected to any end user problem. They are very, very general. And unless you have at least one compelling business use case, it becomes a problem, right?
One thing that's, I'll play my own devil's advocate, trying to stir up a little bit of a fun panel conversation and discussion, is that we end up for some very concrete use cases like chatbots, which are indeed a huge improvement for companies. They spend millions and millions of dollars trying to answer questions of, packages lost and other more complex things. Like food delivery is simple, but imagine you're Cisco and you have all these different configurations. You're trying to automatically do customer support. So that gets a lot harder. And what's interesting is at the end of the day, often the chatbot has only a finite set of actions that they can execute on some database. And so we end up using a lot of knowledge bases for these very applied, focused chatbot applications. And there isn't as much of a use case for some of these common sense neural network types of models, other than helping guide the models in specific sort of decision trees. And then I also thought, as an AI person, we just want to read all the past transcripts and learn everything from data. And then it turns out, no, companies actually want to go very explicit and say, people may have done it in the past wrong. We want to be very prescriptive and say, when they ask this question, then this needs to be the follow-up question. And per regulations of banking and insurance, regulations, you need to then go into this particular node, and it becomes a lot more strict. And this is something that I personally struggle with. That might be music in the ears to some of the folks who are more on the knowledge-based side and less on the neural side.
Yeah, I don't think there's any. Well, at least speaking on behalf of Mark and Mike and me, I don't think we're on any one side. We just would like to see our system get more competent. The thing which it is an interesting point, which is that for all the successes of the neural approaches, it's fascinating that if you look at the so-called assistants, either it's Siri or Google Assistant or Alexa, in large part they're all the natural language the speech understanding is all neural network. But after that, in actually answering the questions, it's, to my knowledge, driven largely by these large corpora of structured knowledge. It's just a fascinating observation. Yeah.
Yeah, we
it's
navigate.
Just, and Mike would be familiar with it. The saying, Mike and Mark, the saying was that if it works, it's not AI. So all that part just works. It's no longer AI.
I think AI works really well for these spatial and temporal signals like Google Photos or speech recognition, like unbelievable.
You see, but that's the interesting thing. All the actual answers that these assistants give you, 10 years ago, that the representing them and keeping this and doing that and drawing the inferences would have been seen as AI. That's not seen as AI anymore. But it's probably a good thing.
So Mark, I'm just wondering, what is the thinking at NIH and NLM about knowledge graphs? Are they willing to look at solutions that involve curation, or they think that, no, this is not the business we want to be in?
Well, there's a lot of excitement about doing as much by machine learning as possible. It's interesting. Particularly since so much of what people do in medicine is based on image understanding, and that's where the big wins have been in the learning community. You can understand that NIH is excited about that until they realize that the accuracy of many learning models and image understanding is about the same as clinicians, which is also about the same as pigeons. You can actually train pigeons to read mammograms pretty well. And that kind of makes people a little bit less enthusiastic. But I think there's also a recognition that so much of what we do just simply cannot be done through learning, because we don't have the gold standards. We don't have the data from which to learn in the first place. And so there is still continued interest in methods that can be hand curated, but of course, the less hand curation, the better.
Okay, that's good to hear. That's good to hear. So one question that comes up in my mind for Guha is that, you talk about these representational problems, you understand their value, but clearly, your focus within Google and within the company is to address specific use cases. What is the mechanism, or what should be the framework using which you could engage some of the academic researchers like Mike and other people like Mike elsewhere to address some of the fundamentally hard knowledge representation problems so that eventually they feed into a system like yours?
Yeah, I kind of like to delude myself into thinking I'm also addressing some of these hard KR problems. But that said, we do try and find every single way in which I can to engage with, especially with Mark and Mike whenever we can. There's others with whom we are trying to actually pick up particular. I've just realized after my bad experience, or I shouldn't say bad experience, after my experience with Psych, where we were not grounded enough in the problems we look at, I've tried to ground my research in particular concrete problems that people who don't care how it's solved would like to see solved. So for example, all this stuff about economics or about COVID or this, they don't really care if the solution is done through kind of symbolic or neural or a combination or what. So that's my where I'm leaning from. And in fact, a lot of the biomedical data commons stuff is not, we provide the infrastructure, talk to them, and it's being built by Sam Picos, who's a grad student, Tony Oro, who's a faculty at Stanford, and with UCSF. So we do, across the board, across with lots of people.
Okay, cool. So Richard, very near the beginning of your talk, you made an interesting remark that that knowledge graphs are being used, but you are kind of not convinced that how they are going to deal some of the more complex problems. Can you tell us a little bit more about that? And if you were to do something to change that going forward in the future research, how would you approach it?
Yeah, it seems like for every domain that's small but useful enough, you can construct a knowledge base and build something useful, for instance, with a chatbot that does order management, or a chatbot that does food delivery, or a chatbot that asks specifically who gets to go back to which office at work, and things like that. And so if the smaller the domain, the more you can construct a perfect knowledge base that solves that problem. And I, part of me wants to just build useful AI technology that makes companies and their customers happier. But part of me also wants to work towards general AGI systems that could answer any kind of question and have natural conversations, and that eventually, are truly intelligent. And so those kinds of systems, I do wonder if and how a discrete knowledge base is part of that overall architecture. And
Well, so I mean, Guha talked about this idea of bringing in the natural language compositionality into knowledge graph design. Do you see any way of doing that using these knowledge graph embedding type approach?
I mean, to some degree, we already did in this 2013 paper that I discussed, where we have compositionality of words, and you can have compositionality of the relationships as well, and then of the overall facts like triplets, you know, entities that are in specific relationships. So there are some simple forms of compositionality too. You know, we have recursive neural networks that I wrote my PhD thesis about that have compositionality both in images as well as in sentences. And so there are definitely ways you can combine it, and we probably have to for real reasoning. What I would like these models to have is a property called end-to-end learnability, where you have a specific objective function, and everything that is part of the model gets learned in order to optimize that objective function. And there, I have a hard time trying to see, as you read a text, ideally, you can construct your knowledge bases yourself. Then, of course, if you read a text, if the text says in the beginning, let's assume the hypothetical world, and then you read all of this stuff, and then you need to know that, like, maybe, you know, 100 pages later, 100 sentences later, that is still a hypothetical fact that at the end of that document is irrelevant, and you shouldn't put it into your knowledge base. So there's a lot of complexity around constructing knowledge base, such that not everything is in some relationship with one another, because that's not that useful in the end either. And there's just so much complexity around the construction of it, and as well as then the, you know, making it actionable, that in the end, I'm starting to think more and more that you just have to be able to memorize the facts in a continuous like neural network kind of vector space, and then get better at retrieving them and reasoning sort of transitively over them, rather than trying to save the original structure of that knowledge and that original representation. But again, right now, for very concrete useful applications, that's just not where the world is at. Largely also because you have to, in the end, call concrete database queries in SQL, for instance, or you have to, you know, run your order management system and click on send a new package out, and those kinds of discrete logical and programmatic structures are harder to access through neural networks.
Mike,
So if I may add a remark to that, I think it can be said that while knowledge graphs, so I have a personal anecdote about my relationship with knowledge, this generation of knowledge graphs. In 1995, I had left Psych. Alan Kay convinced me to come to Apple, and, you know, I had one hammer which I knew, which was knowledge representation, and I was trying to figure out how to apply it to this thing which was literally exploding in size, which is the web. And I was trying to explain all these things to Alan Kay on a whiteboard, sitting in one infinite loop. And I drew this thing where, you know, there was these two nodes and this arc that went between them. And Alan said, stop, that's all that people will understand. Now go create a format for it. And that was this thing called meta content format, which was later submitted to the W3C, you know, as when it went to Netscape, which became RDF. It was pretty clear even in those days that this whole, you know, triples model was just a very base layer. Every one of the KR systems of the past had these multiple layers, which is you had something which recorded these ground atomic formula, and then on top of that you had these layers and layers and layers, and you could say that this micro KG or micro theory event was hypothetical, and it was really far, far, far more complicated. Fast forward, where everybody's talking about KGs, and you go inside any of these big companies, you realize that it's not a triple. I mean, forget triple. You are talking about quintuples, sextuples. You know, you have a temporal dimension, you have a this qualifier, you have a that qualifier. These are complicated structures which are there, and before you can actually solve real problems and answer questions on a large scale, these things becomes quite fairly complicated knowledge representation structures. Not exactly like, but something that you know, somebody from KSL or Margaret Jacks from the 80s would recognize. So I just want to have that, which is that calling these things simple KGs is just these simple triples without being able to do the kind of address the kind of nuances that Richard was correctly referring to. I mean, to solve real problems, these things are really sophisticated. I mean, like, how do you, I mean, Harry Potter is not the same kind of a thing as Richard Searcher. And they kind of live in different worlds, and you have to understand their epistemic status and all of these kinds of things. So it is the case that these knowledge graphs are far, far more than simple graphs today.
Okay.
I have a question for Richard. So you talked about graph embeddings. Are there, when you go into that embedding space, do you see and observe some properties of those graphs which are not evident in the classical representation?
I mean, in some ways, you have just distributional similarities. So you can ask how similar are these two entities, and you'll get some sort of metrics. You get clusters that show you kind of ambiguity. So, when you visualize a bank, for instance, it might be clustered close to sandbank and river, but then also be kind of in between to the financial institutions and things like that. And you can kind of capture some of that ambiguity and visualize it in some sense. So there are some, that is sort of one example, being able to visualize fuzzy sort of similarities. I think Mike had a...
Mike, you want to say something?
You're muted.
Let's see. Yeah, I sort of lost its poignancy at the moment. It was, you were making an argument, I think that Guha definitely addressed one aspect of that, which is that the expressiveness of the representations are much greater, that we're imagining are much greater than just simple graph representations. And so that does account to some extent for the ability to represent things beyond the simple things you were talking about.
Let me add one more poignancy to your comment. And I remember this sitting in a class of yours back in 1989, which is, it is really important to be able, for a system to be able to say, I don't know.
Yeah. And
too many of today's systems, whether it's neural network completions or these graphs, don't really have a way of saying that. And people are, if you look into any of these Alexa's graph or KG's graph, they invent really complicated ways of saying that. And you look at these things and put your heads up and say, God, what have we come? We've kind of reinvented through the back door things that should have been put down in the first place. Yeah.
So yeah, please go
ahead. Sorry, I interrupted Mike. I was just to say that there was a lot of stuff.
That's all right. Vinay's now doing it, so go ahead.
No, go ahead.
My thoughts.
No, I wanted to pose a question to all three panelists. So let's say you were to supervise 3 PhD theses of Stanford students, hypothetically. What would their thesis topics, what would you like their thesis topics to be in the area of knowledge graphs? No answer?
I'll let some other folks go first.
Well, it's really open-ended. I mean, I think my lab tends to be rather applied, and we do a lot of work in knowledge graphs right now.
No, you don't have to think of your lab. Let's just say, you are in computer science. Let's say you're in logic group.
Well, I'll let me just say one thing that comes to mind immediately, because this is one where a company that we're working with wants us to do something which I think is impossible. And it's just the visualization of knowledge graphs, which I mean, I remember being at a workshop in 1986, seeing someone trying to visualize psych. And it was just absolutely absurd, because it was just, the level of complexity was just so enormous. And now that people can build knowledge graphs of just this enormous size, there's this expectation, well, now we should be able to browse them. And I think that's I have no idea how to begin to do that. And I still think there's actually the possibility of a decent dissertation in that, but I'm also nervous because I think it may be an impossible task given where our graphs have gone.
Okay, so that's one.
That's one.
Couple of other ideas?
Yeah. Well, I'll eat my own dog food. I think people have moved into a world where we use knowledge graphs mainly for lookup. We have great applications like chatbots, but they're mainly just doing lookup on a giant graph. And I'd love to see more applications and more theory on how to apply more sophisticated reasoning techniques to what is really a very simple knowledge representation. So I think there's a big win there.
Yeah, it's kind of interesting. I think now that so much research is happening in academia, I do have some folks who in other worlds probably would have done a PhD, and they've been doing for several years now PhD level research, but in a company just getting paid, 10x or more than what they would have as a PhD student, but doing similar work. And if I could, probably would give some of them a PhD. So we, for instance, work on conversational text to SQL challenges. We just published a paper on called CoSQL, a conversational text to SQL challenge, that ideally in the middle of a conversation, you can ask a question and then the system might say, well, there's some ambiguity here in your question, and ask you a question back to try to disambiguate what you actually meant, and then give you finally an answer based on a disambiguated SQL query. And so that is kind of another way of just acknowledging there is a knowledge base or some kind of complex database, which, as you said, could have all kinds of different columns and so on. And then being able to query these databases in natural language is something that I find super fascinating, and that would definitely be one PhD thesis at least worth. In general, sort of generating SQL queries and all their complexity over knowledge bases and databases that you've never seen before, but you have some kind of mapping to is something that's also very interesting. So cross-domain question answering and to text to SQL mapping is another one. And then I think a third thesis is sort of more fundamental on how to be able to learn discrete representations of knowledge in an end-to-end trainable fashion through natural language interactions, sort of the furthest out there.
Oh, it's a fascinating topic. Lua, you want to take a shot?
Sure. I don't know if I have three, but there's one particular topic which is, and this is comes with the caveat, which is that after I finished my PhD thesis, which was on incorporating context into logic and its applications, Nelson came to me and McCarthy and said, "John, you have no idea. That's not a thesis topic. That's a lifetime topic." So topics have to be of a certain size. One particular thing which has been fascinating me for a while, and I wrote a paper on this in 2015, and there was a workshop that a bunch of us organized at the Spring Symposium on figuring out how to combine sort of neural networkish things and symbolic representations-y things, is constructing a model theory out of embeddings. There's no reason why you can't, instead of simple tuples, have vectors and construct a model theory. And it turns out that you can, and you can actually get into things like partial knowledge and so on and so forth. You do run into some hard sort of computational issues. Martin Abadi and I were looking into a bunch of those kinds of things for a while, and then I got distracted. But there's an it is possible to sort of build up a KR out of embeddings as opposed to the traditional tools that logicians used. That would be fascinating, and to see what the properties of those things are. And then, yeah, and in particular, I'm interested in things about partial knowledge and understanding when a system can know that it doesn't know, so that it doesn't try and do completion for everything, etc., etc. So that's my one topic.
Yeah, no, I think those are great topics, and you may recall that this whole idea of system understanding that it doesn't know that it doesn't know, McCarthy called it self-aware system, right? How can we make these knowledge graphs self-aware about what they actually know and what they cannot appropriate? But yeah, that's a great topic. Naren, do we have more questions? We have like 5 minutes left.
We have some very specific questions.
Well, in the last 5 minutes, maybe we should take something more visionary and high
So
level.
I think that can be found by the users. Hey, users, you can use the search engine and find some of those answers.
Yeah. So another sort of high level or visionary question would be, like in your from your respective research area or topics, where do you see this knowledge graph area in next 5 years? And maybe we can, each panelist can take a minute or two, and then that would be a good use of our last 4 minutes this seminar.
I think I covered those with those PhD theses for the next.
Okay,
knowledge.
I mean, again, I could slightly tweak the question. What about where do you see the industry or the products in knowledge graph in next few years? So I mean, thesis means just that's fundamental research, but what about the real world?
Right.
What do you think to see happening? Like what kind of things data commons would be able to do? Or I mean, like same thing for you, Richard or Mark.
Yeah, so I guess a quick concrete answer is what we're seeing is people struggle with creating their own chatbots to query and answer questions that are often founded and based in some concrete database. And so what we want to do is basically generate industry-specific chatbots that have access to knowledge that will then generalize across the whole industry, and basically lower the bar for companies to be able to actually make use of this technology. Because if you ask them, like, here's this perfect system, but you have to train it now for the next year, and you have to set up this whole decision tree manually, you lose a lot of customers in the end. And so I think that is an obvious shortcoming of some of these, and a place where we can help. And you can help with that. You can help it by going through past behavior and past chat transcripts, for instance, and understanding and combining it with what is now called robotic process automation, RPA, where you try to group together what people are doing and then see if you can automate parts of that, so that people can do something that used to take them 20 clicks and one knowledge lookup here, and then changing a knowledge base and then sending an order out or something like that. They can do it in 2 clicks. And those kinds of combinations, again, are kind of fuzzy combinations, because sometimes there's clicking and some writing in the text involved, and then other times they're very concrete things like drop-down menus, select boxes, and writing to some API with some parameters to it. And so again, trying to combine these and understanding that those clicks were really similar. It's just a different browser size window, and so clicking in that area was meant the same thing, together with the structured knowledge, and trying to learn it all for robotic process automation, I think is another really great way to combine knowledge bases.
Cool. So Mark, your final words?
Yeah, I mean, in the short term, I would say the following. As I mentioned, people in biomedicine, where I do most of my work, have religion about symbolic representations. And people are working furiously on creating more and more ontologies for biomedicine. We have, our bioportal system, which is the definitive repository for biomedical ontologies. There's 700 entries. And that's obviously both a bug and a feature, because the idea of having 700 ontologies in biomedicine is just nuts. And I think where knowledge graphs can be very, very important in my area is hopefully providing mechanisms over time for trying to condense some of this information into a more structured, more integrated form. Because I think people who need to be able to take advantage of controlled terminology in particular can't deal with the universe of so many different specific entries. And I think knowledge graphs can be really very helpful here.
Great, awesome. Guha, you want to give your final thoughts?
Sure. One of the things that is happening is that our data we're consuming our data across an increasingly wider range of screen modalities and screen sizes and modalities, which means that the conversion from a machine understandable form to a human understandable form is happening at the last, as delayed as possible, which means that the role of structured data is becoming more and more and more. Today there's over 30 million sites which are making some fraction of their structured data available in schema.org. There's things like Google Assistant and Alexa and Siri, which are only growing in their both in their footprint and in their usage. I think you're going to see sort of every one of these companies I know is trying to figure. They have huge investments in these structured repositories and in their various neural network things, and the relations between the two are not as close as we would like. It would be a fascinating thing to figure out how these two large investments, which often internally collide, not the organizations, but technically there's an impedance mismatch between the two, how they could actually get into much more of a winning symbiosis.
Excellent. I think that's a fantastic point to conclude our series and the seminar. I'm really grateful to all three of our panelists today for illuminating us with their insights and visions for the future. And I also want to thank all the participants in the seminar who have been very faithful and have been showing up and contributing to the dialogue here. Thank you all. And in next few days, we'll be sending out a survey. And please feel free to give us your feedback and your thoughts on how we can improve the series. And hopefully we will be back next year. Thank you all very much.
Thank you, Vinay. Thank you, Naren.
Thank you, folks.
Thank you, everyone.
Bye.
Talk
Right,
soon.
right,